problem to cover. So let's go ahead and cover that real quick. The third problem was about target practice. So in this problem, we have t less than equal to 10 to the 5 targets and c less than equal to 10 to the 5 commands. So we have a number line. There is a number line. There is a number line. You initially start at position 0, and then you basically go through all the commands one by one. Each one, you have a string of commands you go through. Each one can be one of 3 options, F, L, or R. L and R just means that you move 1 to the left or 1 to the right. And then F means that you fire at the current position. And if it hits a target, then you get if it hits a target, then yeah, you hit a target. Yeah. And so now, basically what you want to do is you want to calculate the number of distinct. So you only count if you fire the target multiple times, you only count it once. So you want the number of distinct targets that you hit. And also, you don't just want to calculate this. You are allowed to, you want to maximize the number of distinct targets you hit if you are allowed, if you can change at most one command in the sequence. So at most once, you are allowed to go into the sequence and you can change like an L to an R or change an L to an F or make some sort of change to try to maximize the number of distinct targets that you hit. Okay, so that's the problem. Let's talk about how to solve it now. So I'm going to say right now that there are many different solutions to this problem, many different solutions that I know of, and they are of varying levels of implementation difficulty. So I'll present a solution that I think is relatively clean and short to implement. It's like probably less than 100 lines, which is considered short for this problem. So let's do this. So first thing we can observe is that so the first observation we can make is that the ending coordinate can shift by at most plus or minus 2. You can't shift more than that. The way you can shift 2 is if you change an L to an R. If you change an L to an R, then instead of moving to the left by once, you will instead of moving left once, you will move to the right an extra time. And so your overall ending coordinate will be a +2. If you move from a right to change the L to R to L, that's a -2. And then everything in between can be done with some sort of other change. So the point is that either ending coordinates can shift by at most plus or minus 2. And so what we can do is let's just fix what the ending coordinate is. There are most 5 options. We'll just run the same algorithm 5 times. So what we'll do is we'll fix the ending coordinate. And now the second thing is there's this tricky thing about distinct targets, right? We have a distinct, we only want to count each target at most once. That's kind of finicky. So as an aside, let's prepare a subproblem of I have this black box data structure. Where what I can do is I can add some x, I can remove one occurrence of x, and I can count the number of x with at least one occurrence inside the data structure, right? This is just a subproblem. And this subproblem can be supported in O of 1 for every operation. Because what you do is you simply have a frequency table. You have a frequency table. And then when you have an x, you just plus like frequency of x or like minus minus frequency of x if you add or remove an element. And then when it drops to 0 or when it goes to 1, you plus 1 or minus 1 from your count. So you also keep track of the count, like plus the count. So that's our subproblem here. We have this data structure that's able to just kind of black box, like add elements, remove elements, and count the number of occurrences, count the number of x with at least one occurrence. Okay, so why do we care about this? Now let's actually talk about the algorithm itself. So we fixed the ending coordinate, right? We fixed the ending coordinate. So what we'll do is we'll first walk from the ending coordinate backwards. So we'll first simulate backwards from the ending coordinates that we fixed. And we'll just add all the targets that we hit. We add all the targets that we hit into our data structure. And we don't have to worry about like making sure we only add a target at least we don't have to worry about adding a target like at most once, because our data structure, this black box, already takes care of that counting for us. It already takes care of the annoying part of like making sure that we only count a target once if it's hit multiple times. So we actually just add it every single time and let the data structure do its work, right? So we add all the targets to our data structure. And now what we'll do is we're going to sweep from the front. We're going to sweep from the front for where we change. So we have the sweep line here. It's moving to the right. And as we move to the right, we are going to, as we move to the right, we're going to remove the targets that we hit from the back, like based on the ending coordinate simulation, and we're going to add the ones that we hit from the front. And then at each coordinates, we just manually like try, like we brute force iterate over every single possible change, and we allow the change as long as it would cause for the alignment to be correct, as long as it would result in the ending coordinate that we fixed at the very beginning. So we just sweep from left to right. We as we sweep, we add the coordinates based on the start, and we remove the coordinate based on the end. And then we just try at each position all the changes. When we sweep to the points, we also try all the changes. So we try like changing like say we change an L to an F, then what we can do is we can just add this coordinates to the black box, data structure, query the data structure for the answer, and then roll it back. So just remove it from the data structure, and then keep going. And then similarly, if we change like L to R, in this case, there's no adding to the data structure. But the point is that like if you do like an F, if we change like say an L to an F, we can just add our current coordinate to the data structure, check the answers, take the maximum of the best, take the maximum with the current answer so far, and then roll it back and then keep sweeping. And so with this solution, this would work in O of n time. So there's a constant amount of work where we have like a constant factor of 5 for each ending coordinate. We have a constant factor of 3 for everything we change into. But other than that, it's all O of n. And yeah, the reason I present this solution is because I think the trickiest part of this problem was trying to get the distinct coordinate stuff correct. And you might have had issues where like if you pre-compute from the prefix or suffix and then you change to something in the middle has to be like treated differently than like the beginning or the end. So this data structure kind of like gets rid of or does all that work automatically for us, so we don't have to like worry about the details of what happens with that. And this works in O of n. Yeah. So any questions?
There's some discussions on the chat.
Yeah, I'm reading the chat now. Yeah. I'll scroll to the top. There's a lot to read.
Take your time.
Yeah, so what black box being used? Yeah, so you can use a map, that's fine. Or you can just use like a giant array. The frequency table can just be a giant array of like size like 2 times C plus 1, because you can go to at most negative C or positive C. So it could just be a giant like array. How do we check the duplicates in O of n? So that's what the data structure is. So the idea is that I can add something multiple times, but maintain this counter that only counts it once. So the idea is that when I do like plus plus the frequency of some element, if it hits 1 for the first time, then I do like count plus plus. Right. And similarly, if I do minus minus the frequency, if I reduce the frequency of some element, then it hits 0, then I decrement the count by 1. So that's how the data structure maintains the count of duplicates. Yeah, someone said this is their solution, but it's just a bug somewhere. Yeah, definitely the tricky part of this problem was definitely uh trying to implement this correctly with no bugs. And they're actually like this is I mean, and then that also depends on what algorithm you choose as well. Some algorithms can get a little bit, some like other solutions can get messier. Yeah, what alternative solutions are there? Um, so like one other solution I had in mind is like to do some sort of like calculate a prefix and suffix and then like use some sort of use some sort of like table to check like only count it like +1 if it's the first occurrence or from the front or the last occurrence from the back. And they do some casework on what happens if we change. But that gets messy fast. That there are probably also other ways you can like deal with this condition or try to count this. Yeah. Yeah, so that's why I like this approach because it kind of relegates the work of dealing with duplicates to the black box data structure, and then we just sweep and try. We just sweep and try every point. All right. Any questions on this problem or any of the problems that that we covered? Yeah, still kind of confused while we roll back. Yeah. Um, I guess I can give you a little more concrete examples. The idea is that if let's say you sweep from the back and the coordinates are like let's say the coordinates are like let's say from the front the coordinates are 0, 1, 2, 1, 0, -1, -1, 0, 0, and 1. But now we sweep from the back, we shifted by 2, so it's gonna be like 3, 2, 2, 1, 1, 2, 3, 4, 3, and 2. And what happens is initially we sweep from we go from the back and we add everything to our data structure based on these coordinates. And then when we sweep from the front, we add these coordinates and we remove these coordinates. And then we just need to make sure that whenever we make a change, the change needs to be such that it like lines up. So we're trying each position and making a change. Yeah, so that's the interesting thing. So our data structure is already, so at any point, our data structure will already have the entire suffix and this prefix so far inserted, and it will have automatically computed like the number of duplicates. What do I mean by line up? So yeah, as an example, here we have fixed the ending coordinates to shift by 2. So it needs to be changed. So it needs to be that we change like, we need to change like an L to an R. That's the only way we can get a shift by 2. And so at any point, we only allow changing, like say an L to an R. That's the only valid change. So we don't like allow like if we for example change like an F to an R, that doesn't create the right ending coordinate. So we can't count that as like we can't count that as a possibility. So that's what I mean by line up is that like when we consider a sweeping, we only consider changes that cause like the correct ending coordinate. Yes, we can just loop through the possible changes. There are only almost 3 for every coordinate. Yeah, and then there are end positions where we can change it. Yeah, and we already fixed the ending coordinate out in the outer loop. Like there's an outer this entire algorithm is being run 5 times, once for each outer once this entire algorithm is being run 5 times, once for each ending coordinate. Yeah, how do you add all the positions at once? Yeah, so the idea it's like we add all of these coordinates first, and then when we sweep from the left, yeah, we sweep and then when we sweep from the left, we start adding these coordinates and start removing these coordinates. And what I was talking about the rollback was that let's say we change an L to an F. then this is like an extra fire that's not accounted for. So when we change the L to an F, we first add the F, we add the current coordinate based on the F, we check our answer, and then we remove the F. So we change it back to an L, and then we keep going to the next position. So that's what I was talking about with the rollback. Is like sometimes if you consider changing to an F, you may have to temporarily add like a new coordinate and then remove new coordinate for this particular case, and then consider the answer, and then take it out and keep going. Am I sweeping on -2, 2, 1, -1? Where did those numbers come from? Or oh, so that's actually that's the offset. We fixed the offset on the outside. So we run this algorithm like 5 times in total, like once for each possible like amount of offset, like 0, 0, 1, -1, 2, and -2. Yeah. So maybe I could write some quick pseudocode to show how this works overall. So basically, do like a for loop for each ending coordinate. Yeah, for each ending coordinate, 5. We first go backwards and add all to our data structure, and now go forwards. So like I say, I from 1 to n, and for each one, we iterate for each of you can actually do this a little more efficiently, but it doesn't really matter. The way I did it was I just iterate over for each F, L, and R. Try the change. If the offset is correct, then the answer is going to be the maximum of the answer. We update our answer with the current like data structure like value. DS count. So this is at most 3. This part's at most 5. This part's like n. So this is O of n. Yeah. Yeah, and the 3 per string is just like I'm trying like for each position. Actually, I guess you don't have to try all the possible characters because only some of them are going to be like valid. But I mean, I was just being a little like simplistic with the explain with demonstrating this. Since it's all like O of n anyway, so it doesn't really matter if you do an extra factor of 3 or whatever. No, we only make at most one change, right? So there are n places we can possibly change, and each one can change to 3 options. That's 3n. So that's fine. Yeah, so there are at most n possible locations. Yeah. So n possible locations for a change and 3 for each. Yeah, so it's 3n, which is still O of n. Mm. How does reverse sweep accurately account for move to right for all other commands? So I guess going back to this diagram here, the reverse sweep is the first like put all of the reverse sweep is the first put all of the coordinates based on the ending coordinate, all the coordinates into the data structure, where these coordinates are based on the ending coordinate. And then these ones are based on the starting coordinate. And so when you like start sweeping from the left, you're adding these elements and you're removing these elements. And you just need to make sure that the change is such that like you need to make a change. Like here, at some point you need to go from like the 2 bridge over to this 3, right? So you just need to make sure that like the change you make like is appropriate, like it gets you to the correct offset. So that's the part. So that's how you're like linking these two sequences up basically. It's like you're changing, like say this is an L and you change it to an R, that's valid. So that will get you to this. If you replace this from an L to an R, so that's like the middle part here, then this part is now bridged with this part. There are multiple targets, how they switch to work. Oh, you don't do it, you don't do this once for each target. It's like your target is just like the target is just like when you add it, I guess you also have to check like is this coordinate like a target? Yeah, that's just like a quick if check. So at the very beginning, you just like have like a Boolean array of like target of X is true if there was a target at coordinate X and false otherwise. And then you just like when you add it, you just need to make sure you only like count it if it's actually a target there in the first place. Otherwise, you can just ignore it altogether. Yeah, any other questions? Yeah. I think this one was undoubtedly the hardest of the three. Just because like even if you get the right idea, you still might have like not be able to like fully implement it. Mm. Okay. Then I think let's go. I'll stop screen, share my screen, then we can go back to the slides. Yeah.
Yeah, thank you, Max. We have 2 more slides to share here. Here is the summary page. How the Max just give us a quick summary of these 3 problems and the corresponding XCamp courses.
Yeah, so I put some, I guess you can say tags here for what topics you might need to be able to solve these problems. And then there's some classes here that go with it, or there's some courses here on the right that go with it as well. Yeah, and we have a Discord that you can join for more live solution discussion if you want to keep discussing these problems. Yeah.
Yeah, thank you, Max. Let me copy this to the chat. Please join our Discord channel. So we will post even the future events, future activities here. Also, please, fill in a form about your scores, so we can give you. Here, I think here's in the next slides. We can give you a detailed report card. So here's the link. You can see it's in the chat too. So after this contest, I think all of you kind of eager to know kind of some analysis on the result. Please share with you your score for each problem, so we can give you a pretty detailed report like here. In addition, at XCamp, we provide a series of classes. First is onsite camp is coming. It's from 26th to the 30th in San Jose. It's 1 week from 9 to 5. If you want to improve your coding, especially the competitive coding, the USACO results in the coming sessions, please join our onsite camp. It's very effective. It can be improved. Also, we have a year-round weekend class, especially we have grandmaster classes for USACO Gold, Platinum, and US Camp, also even at the ROI level. APCS is another one if you need any help on that. Okay, great. Thanks again. Thank you, Max, for the solution session. Maybe last call. Any other questions? No? Okay. Thank you all. Wish you a great holidays. Okay. Thank you, Max.